Let's learn about the quotient rule in calculus, a formula for finding the derivative of one function divided by another function. Let's say we have two functions, u of x and v of x. When we divide these functions, we get u over v. To find the derivative of this quotient, we use the quotient rule. The formula states that the derivative of u over v equals v times the derivative of u minus u times the derivative of v, all divided by v squared. Let's break this down step by step. First, we need the derivative of the numerator function u, which we call du dx. Then we need the derivative of the denominator function v, which we call dv dx. Now, let's visualize how the formula works. In the numerator, we multiply v by the derivative of u, then subtract u times the derivative of v. Finally, we divide everything by v squared. Here's an easy way to remember the quotient rule. The denominator is always v squared. In the numerator, think v do minus u dv. This pattern, v do minus u dv over v squared, is the key to the quotient rule. Let's see why this makes sense. When we have a fraction and both the top and bottom are changing, we need to account for both changes. The v do term represents how the numerator is changing, while the u dv term represents how the denominator is changing. We divide by v squared because we're dealing with a fraction, and changes in the denominator affect the whole fraction quadratically. In conclusion, the quotient rule is a powerful tool for finding the derivative of a fraction where both the numerator and denominator are functions. Remember the pattern, v do minus u dv, all over v squared. Welcome! Today we're going to prove the quotient rule in calculus. The quotient rule tells us how to find the derivative of a fraction where both the numerator and denominator are functions. Let's start by defining our function f of x as u of x divided by v of x, where both u and v are differentiable functions. Our goal is to find the derivative of this quotient. To find this derivative, we'll use the limit definition of the derivative. The derivative is equal to the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. Now, let's substitute the expressions for f of x plus h and f of x. F of x plus h is u of x plus h divided by v of x plus h, and f of x is u of x divided by v of x. To subtract these fractions, we need a common denominator. We multiply the first fraction by v of x over v of x, and the second by v of x plus h over v of x plus h. Now comes the clever part. We'll add and subtract u of x times v of x to the numerator. This doesn't change the value, but it helps us group terms in a useful way. Let's factor this expression. The numerator can be written as v of x times the difference of u minus u of x times the difference of v. Now we can separate this limit. As h approaches 0, v of x plus h approaches v of x, so the denominator becomes v squared. The remaining terms in brackets are the limit definitions of the derivatives of u and v. Finally, we recognize these limits as the derivatives of u and v. This gives us our final result. The derivative of u over v equals v times the derivative of u minus u times the derivative of v, all divided by v squared. Let's see a quick example of how this works. Suppose we want to differentiate x squared over x plus 1. Here, u of x is x squared, and v of x is x plus 1. The derivative of x squared is 2x, and the derivative of x plus 1 is 1. Plugging these into our formula, we get x plus 1 times 2x minus x squared times 1, all over x plus 1 squared. This simplifies to 2x squared plus 2x minus x squared, all over x plus 1 squared, which further simplifies to 2x over x plus 1 squared. And that completes our proof and example of the quotient rule. Remember, this rule allows us to find the derivative of any quotient of differentiable functions. It's a powerful tool in calculus that you'll use frequently in your studies.